Welcome to the course on An Introduction to Information Theory. I am Adrish Banerjee, and today we are going to start a new topic, that is on source compression, block to variable length coding. So our input block size is fixed and we get compression by varying the output block size depending on the probability of occurrence of this block. So in this lecture we are first going to talk about what do we mean by a prefix-free code and how we can, what is the condition for the existence of a prefix-free code. So we'll first motivate this problem of block to variable length coding for a single random variable, and then we'll define what we mean by uniquely decodable code and a prefix-free code, and then we'll talk about Kraft's inequality, which talks about the existence of prefix-free code, condition for existence for prefix-free code. So this is the system model that we are looking at. We have a message source that we want to compress into set of code words Z. So we have our information. So this is a source that we want to compress. So this is input to our source encoder, and output of the source encoder is the set of code words which we denote by Z. Now U is a k-ary random variable. That means U takes k different possible values. Let's just call them U1, U2, U3, UK. So these are the k possible values U takes with some probability, P of U1, P of U2 and P of UK. Now our output code word consists of d-ary alphabet, where d can be different from k, and the length of the code word, which we are denoting by W, is a random variable. So that's variable length. Okay, so W is a random variable. As a result, our output set of code words have variable length. So a list of code words is then denoted by this ZIs. So ZIs are d-ary sequence, and these are essentially code word corresponding to our input, which is a k-ary input, denoted by U1, U2, U3, UK. Now let us assume that ZI is the code word corresponding to the source UI, and let us denote by WI the length of this code word. So this ZI is XI1, XI2 up to XIWI. So WI is the length of this code word ZI, which is a code word corresponding to UI. So then what is the average code word length? Average code word length is basically given by length of the code word for UI, probability of occurrence of UI, and this we sum over all k-ary alphabets of U. So this is my average code word length. Now when I am doing block to variable length coding, I want this average code word length to be low. We will subsequently see what's the minimum number of bits required to reproduce the source losslessly. So then the smallness of this average code word length is a measure of how good my source encoder is. So if I can represent my source U in smaller number of bits without losing information, then that's a better source encoder. So our objective is to find what's the minimum code word length required to encode a source U. Now let us move into defining what do we mean by a uniquely decodable code and what is a prefix-free code. So a code is uniquely decodable if for every finite sequence of code corresponds to at most one message. So we can uniquely decode if a finite sequence of code corresponds to only at one message. Now, one way to ensure unique decodability is to ensure that no code word is a prefix of another code word. So if we can ensure that no code word is a prefix of any other code word, then we can ensure unique decodability. And what do we mean by prefix of another code word? So let's say you have a DRE sequence Z. Now it is a prefix of another DRE sequence Z dash if Z is of length L and the first n bits of Z dash are exactly same as that of Z. So let's just take an example. Let's say Z is 0 1 0 and let's say Z dash is 1 0 1 1 0. Now you can see Z is not a prefix of, it is not a prefix of Z dash because 0 1 0, this Z dash does not start with 0 1 0. But if I consider any other code word, let's say Z is 1 1 1 0 1, then you can see that the first three bits of this Z dash is same as this Z. So in this case Z is a prefix of Z dash. So we say a DRE sequence is a prefix of another DRE sequence Z dash if Z is of length n, when obviously n is greater than or equal to 1 and the first n bits of Z dash are exactly same as the sequence Z. Now if we want instantaneous decodability, please note that in this we are talking about variable length codes. So when we are talking about variable length codes, we need to know where the code boundaries are, right? For example, if your code word is 0 1 0 1 1 0 1 1 1. Now if I have a string of code words, just write something. Let's just see 1 1 0 1 1 1. Now note here, if this is a set of code words that I have, code word corresponding to U1, code word corresponding to U2, code word corresponding to U3, code word corresponding to U4, and this is the coded sequence that I am sending, then I can easily find out what these code words are. So look, 0 corresponds to code word of U1, then 1, there's no code word with 1, 1 0, yes, this is this code word, right? Now 1 1 0, that's another code word, 1 1 1, that's another code word, 0, that's another code word, 1 1 1, that's another code word. So you can see I know precisely where these code boundaries are. So I can do instantaneous decodability as opposed to if I, let's say, change the code words to, let's say, 0 1 1 and 1 1 0 and let's say 0 1. If I change it something like this, let's say this is my code word, let's say this is my set of code words, then in this case you can see if I get 1 1, I will have to wait and see what the next bit is. If the next bit is a single 0, then it's probably this code word. If there are even number of zeros, then probably this code word has been transmitted. So in this particular example, this is an example of a code which is not instantaneous decodable, because I will have to look beyond what I have received to actually decode back the sequence. Whereas in this particular example, when I get a 0, I exactly know that this is a code word for U1. When I get 1, I know I need to look further. When I get 1 0, I know exactly that this is a code word corresponding to U2. Whereas in this particular example, if I get 1 1, I am not able to make a decision whether this code word is transmitted or this code word. I need to go further to make a decision. So in case of instantaneous decodability, these code boundaries are exactly known. So I can just decode the code word right there. So no code word should be a prefix of another code word if you want your code to be instantaneous decodable. And you can see in this particular example, none of these code words are prefix of any other code. This code word is 0. You can see none of these 3 code words have 0 as prefix. This has 1 0. Again, these 2 code words do not have 1 0 as its prefix. And this is 1 1 0 and 1 1 1. They are not prefix of any other code word. So for instantaneous decodability, we want this condition that no code word should be prefix of another code word. Now, code that satisfies this property that no code word is a prefix of any other code word, this particular code is known as prefix-free code. And as we can see from the example that we did, a prefix-free code can be instantaneously decoded. So this is an example of a prefix-free code. You can see code word corresponding to U1 is 0, code word corresponding to U2 is 1 0, and code word corresponding to U3 is 1 1. Now, if I get any set of sequence, let's just call it, this is 0 1 0 1 1 0 1 0. You can see I can exactly find out what the code words are. So this is the code word corresponding to U1. This is the code word corresponding to U2. This is the code word corresponding to U3. This is the code word corresponding to U1. This is the code word corresponding to U2. Right? Now look at this example. Is this a prefix-free code? No. Why? Because U1 code is 1, and you can see U1 is a prefix of this code word U3, because U1 is 1 and U3 also starts with 1. So then this particular code is not prefix-free. Now the question is, can we decode a non-prefix-free code? The answer is yes, but they cannot be instantaneously decodable. So in the next slide we will talk about the condition for uniquely decodable code. Now let's just take an example. So let's say we have a set of code words, right? And if say they corresponds to, this is a set of partitioning of the code words, let's say A1, A2, A3, A4. And let's say I can have another set of code words corresponding to the same bits, call it B1, let's say B2, B3, B4. This is an example where set of string, basically it can, a set of code words can be partitioned in 2 different ways. One is A1, A2, A3, A4, another is B1, B2, B3, B4. So this is a case of code not being uniquely decodable. Now look at what is the condition that we are getting when the code is not uniquely decodable. One thing that we can see here is there's one code word which is a prefix of another code word. Here you can see A1 is a prefix of this code word B1. And then whatever the dangling suffix, the suffix which is, if from B1 I remove A1, so whatever suffix is remaining, I can see this suffix is a prefix of another code word A2. This is a prefix of another code word A2, right? So what I can see here is, in the case when the code is not uniquely decodable, it's not a prefix-free code, and whatever suffix is remaining from particular after you take out the prefix, that suffix is then again part of a another code word. That's a prefix of another code word, right? So the test for uniquely decodable code word can then be written as follows. Let us assume that we denote by S0 the set of original code words, and we want to find out whether these set of code words are basically are uniquely decodable. So we construct a set of sequence of sets S0, S1, S2 as follows. If a code word WI in S0 is a prefix of another code word, so if it's a prefix of another code word, then we would have another code word WJ, which would be of the form WIA, where WI is basically a code word in S0 and A is some suffix in S1. So if we have a code word WI in S0 which is prefix of another code word, then what we do is we place this suffix. So after you remove this prefix WI, whatever is remain is suffix. So we put this suffix A in S1. Okay. Now to explain this, let's just fast forward and look at this example. So I have this set of code words A, C, AD, ABB, BAD, DEB and BBCDE. Now let's look at these code words and see if any of these code words are prefixed to any other code word. So let's look at this A. Is A prefix to any other code word? Yes, it's a prefix to AD, it's a prefix to ABB. So what is the suffix left if I remove this prefix? That's D. So I put this D in this set S1. Next here, if I remove this prefix A, what is left is this suffix BB, and I put this BB in S1. Any other code word? I don't see any code word which has C as prefix. Any of these code words. Similarly, BD, BAD, there is no code word which has BAD as is prefix. So S1 will have B and D, D and BB. So that's what I meant. If you have a code word WY in S0 which is a prefix of another code word, then you put this suffix in this set S1. Okay. Now in general we will form this set Sn in this fashion. We will compare S0 and Sn minus 1. If there is a code word in S0 which is a prefix of another code word in Sn minus 1 or vice versa, we place the suffix in Sn. So how do we form this set Sn? We look at S0, code words in S0 and code word in Sn minus 1, and if any code in S0 is a prefix of any code word in Sn minus 1 or any code word in Sn minus 1 is a prefix of any code word in S0, then we take the suffix out and place it in this set Sn. So let's go back to our example. So how do we get this set S2? So we need to compare this set S0 and S1. Okay, we need to compare this set S0 and S1. So what do we have here? So let's look at A. Do we have any code words in S1 which has A as prefix? No, we don't see the same thing with C, AD, AB, BAD, DEB, BBCD. We don't see any of these code words being prefix of any code words in S1. Now look at code words in S1. D. Do we have any code word here which has D as its prefix? The answer is yes, and that's this code word. Okay, so then what we will do? We will remove this prefix and we will put this suffix in set S2. Any other code words in S0 which are starting with D? No. What about BB? Do we have any code word in S0 which start with BB? The answer is yes, that's this one. Now what do? We remove this prefix and we put this suffix, which is CDE, in this set S2. So this is how we get our set S2. Now how will we get our set S3? Again, we are going to compare S0 and S1. We'll first try to see, is there any code word in S0 which is a prefix of code word in S2, or is there any code word in S2 which is a prefix of code word in S0. So let's look here. So we can see here S0 has code word C and this has a code word CDE. So clearly C is a prefix of CDE. Then what is the suffix? The suffix is DE, and we put this suffix here in the set S3. Is there any other code word? You can check. A is not a prefix of EB or CDE. AD is not a prefix of any of these two code words. Similarly, none of these code words are prefix of these code words. And we can check EB. There is no code word in S0 which starts with EB. Similarly, there is no code word in S0 which starts with CDE. So S3 will only consist of DE. Now how do we find this set S4? We are now going to compare S0 with S3. So compare S0 with S3. Now so DE, right? Do we have any code word in S0 which starts with D, which has prefix DE? The answer is yes, that's this one. So if we remove this prefix DE, the suffix that is left is B. So then S4 will be B. Do we have any code word in S0 which is a prefix of code word in S3? We can check A, C, AD, ABB. None of these are prefix to DE. So S4 consists of only B. Now in the similar fashion we can find this set S5. So we look at code words in S0 and we look at this code word in S4. Now any of these code words been prefixed to this code word? No. Let's look at code words in S0 which starts with B. So that is one of them is this BAD. So the suffix here is AD. So this AD is here, and the next code word is BBCDE. So here the suffix is BCDE. So this BCDE comes in set S5. How do we find this set S6? Again, we are going to look at these code words and compare it with these code words. And we will try to find out if any code word in S0 is a prefix of code word in S5, or is there any code word in S5 which is a prefix of a code word in S0. So we can see A is a prefix, and that's the only prefix that we can find. A is a prefix of AD. So the suffix here in this case is D. So this S6 is D. And similarly we can find out S7, because if we compare S0 and S6, we see there is a code word here DEB, which has D as prefix. So the suffix is EB. Now do we have any code word in S7 or S0 which is a prefix of each other? So is there any code word in S0 which is a prefix of code word in S7? The answer is no, because we don't have any code word here starting with E. Similarly, there is no code word in S0 starting with EB. So we stop here. Okay, so this is how we find these set S1, S2, S3, S of n. Now once we have found the set, a code is uniquely decodable if and only if none of these sets S1, S2, S3, Sn contains a code word that is a member of S0. So the condition that we want is none of these code words like D, BB, EB, CD, D, B, none of these should be part of S0. So let's look at these code words in S1, S2, S3, S4, S7, and they should not have anything common with S0. Now that's not the case here. You can see S5 has AD and S0 also has AD. So this is not a uniquely decodable code. Now we have described what is a prefix-free code, that no code word should be prefix of any other code word. Now this prefix-free code, we can also represent it using a D-array tree. So let us define what is a D-array tree. So a D-array tree is a finite rooted tree such that there are D branches stemming onwards from each node. So let us take an example. Let's say D is equal to 2. So that's a binary tree. So binary tree will be something like this. So this is my root, and there are 2 branches stemming from each node. So from the root node there are 2 branches, from this there are 2 branches. So a D-array tree is a finite rooted tree such that there are D branches stemming from each node. These are nodes, leaves. We say a D-array tree is full of length n if it is a D-array tree with D raised power n leaves at depth of n from the root. So let us define first what do we mean by depth and what do we mean by leaves. So you have a tree, this is the root, and it's a D-array tree, so there are D branches stemming from each node. Let us consider the example of D equal to 2, a binary tree. So there are 2 branches stemming from each node. This is a root node, so there are 2 branches coming from this node. So this is, depth is defined as how far from the root these leaves are. So this is at depth 1. Now leaf is basically a node from where there is no further branches stemming, right? So if I draw a tree like this, this has basically 2 branches and these are my leaves. Now if I draw a tree like this, you can see these nodes are at depth 1, and then you have leaves at depth 2. The leaves are basically nodes from which there is no branch getting out, and this is depth 1, this is depth 2. Similarly, I can have this is a binary tree up to depth 3, and there are 8 leaves possible at depth 3. So a D-array tree of length n is full if it has d raised to power n leaves at the depth. So for example, if I draw a tree like this, if I draw a tree like this is not a full tree of length 2. Why? Because I don't have 4 leaves here. I only have, this is only extended up to depth. This particular branch is only extended up to depth 1 from the root. So this is not a full tree. However, if I extend these node and I have something like this, then it is a full tree because I have 4 leaves at depth 2. So a full tree will have all d raised power n leaves. So it is all the nodes are extended up to depth n. That's a full deary tree of length n. Now a deary prefix-free code can be identified by a set of leaves in a deary tree. So the claim I am making is we can identify a deary prefix-free code from the set of leaves of a deary tree. Let's take an example. So I have code words. Let me write Z1 is 0 1 1, Z2 is 1 0, Z3 is 1 1 and Z4 is 0 0. Now you can see that none of these code words Z1, Z2, Z3, Z4 are prefix of each other, and we can see that since none of them is prefix of each other, each one of them can be represented using this deary tree. So here I have binary bits, zeros and ones, so I can consider a binary tree. So and the maximum length of the code word is 3, so I will extend up to maximum 3. So let's see, I want Z1. Z1 is 0 1 1, so I extend this root node to 0 and 1. Then to get 0 1 1, I extend this node 0 to 0 0 and 0 1. So I get 0 1 and then I extend it to 1. So that's my Z1. Similarly, how do I get Z0? I have this 1 and then I take this leaf 1 0, that's my Z2. Z3 is 1 1, that's this, and Z4 is given by this. So you can see from the root there is a unique path. Path from root to Z1 is this, and there is no code word along this part. Similarly, path from root to Z2 is unique. There is no code word in this path. Z3 there is a unique path from root. Z4 there is a unique path from root. So we can represent these prefix-free code as leaves of a deary tree. Now, having represented a prefix-free code using a deary tree, now let us prove what is the condition for existence of a prefix-free code. So the Kraft inequality talks about when does a prefix-free code exist. So it says there exists a deary prefix-free code whose code word lengths are given by W1, W2, W3, Wk if and only if this condition holds. So what does it mean? It means that if there exists a prefix-free code which has code word length given by W1, W2, Wk, then this relationship must hold, and if this relationship holds and there are code words of length W1, W2, Wl, then that code must be a prefix-free code. So let us prove this. Now what we have shown so far is we can represent a prefix-free code using a rooted de-array tree. So if you have a full de-array tree, now again what is a full de-array tree of length n? It is a tree which has d raised power n leaves. So all the nodes are extended up to length n. So in a full de-array tree, the number of leaves stemming from each node at depth w is given by dn minus w. We can see this. Let's just draw a binary tree. I'm just drawing a binary tree of depth 3. This is a full de-array tree of length 3, okay, and these are my 8 leaves. Now you can see that if you look at nodes at depth 2, which is this node and this node, right, n in this case is 3, d in this case is 2. Now let us look at nodes at depth 2, which is this node and this node, this node. Now take any node. Let's say we take this node. Now how many leaves are stemming from this particular node? That is this leaf and this leaf, that is 2. And this is what we get from here. D is 2, n is 3, w here is 2. So there are 2 leaves which are stemming from this node. Similarly, you can take from any. This is again another node at depth 2. There are 2 leaves which are stemming from this node, and this is what I am claiming here. Now take a node at depth 1. So let's take this. So this is corresponding to w equal to 1. Now how many nodes, how many leaves are stemming from this node? That's this 1, 2, 3 and 4. You can see this is one leaf, this is one leaf, this is one leaf and this is one leaf. So there are 4 leaves which are stemming from this node at depth 1, and you can again check d is 2, n is 3, w is 1, so that should be 2 to the power 2, that should be 4, and that's what we are getting. So if you have a full de-array tree of length n, you have d raised to power n minus w leaves which are stemming from each node at depth w, where obviously w is less than n. So suppose there exists a de-array prefix-free code. So we are first trying to prove that if there exists a de-array prefix-free code whose code word lengths are w1, w2, wk, then this condition must be satisfied. So we are saying there exists, let's say there exists a prefix-free code, de-array prefix-free code. So if there exists a de-array prefix-free code, we can construct a de-array tree corresponding to this prefix-free code. And how do we construct this tree? We construct this tree by pruning its full de-array tree of length n when n is a maximum of w1, w2, wk, and we are going to prune it at length w1, w2, w3, wk. We are going to prune that, right? So that's how we are going to get a prefix-free, a de-array tree representation of a prefix-free code. For example, if you look at this particular case, now here we require a prefix-free code of length 3, 2, 2 and 2. So how do we get it? We can construct a de-array tree up to depth 3, and then we start pruning them at, so to get z1 I1, 2, 3. So this is, I just pruned that, so I just prune the tree at 3. Then for Z2 I just prune the trees, so I do not take into account the other 2 leaves which are stemming from this node Z2, right. So to construct a prefix, to construct a DRE tree corresponding to this prefix free code, as I said, I will first construct a full DRE tree, right, of depth 3, because maximum code word length is 3. So this is my DRE tree of depth of length 3. Now I can assign these code words by pruning the tree at appropriate level. So for example, for Z3 I need 1 and 2, so I just prune this tree here. For Z2 again I need 1 and 2, so I just prune this tree here. For Z1 I need 3, so I have 1, 2, 3. So just let me just write it as well. This can be, let's say this can be Z3, this can be Z2, this can be Z1, and then for Z4 again I need 2, so I can just take this and this, I can just prune this tree. So this can be Z4. Okay, so these are my leaves corresponding to my prefix free code, and this is an unused leaf. I am not using this leaf. So I hope it's clear how we can map a prefix free code to a DRE tree of length n, and this we do it by pruning the DRE tree at appropriate length W1, W2, W3, Wk. Now due to prefix free nature of this code, if at Wi I delete this many leaves, none of these leaves would have been previously deleted. Why? Because my code word is prefix free, so there is only one path from the root to this particular code word. So this dn minus wi leaves that I am pruning to construct to map a prefix free code of length wi, those leaves would not have been removed earlier. So then to map a prefix free code of length W1, I am deleting so many leaves. To map a prefix free code of length W2, I am deleting so many leaves. To map a prefix free code of length Wk, I am deleting so many leaves. Now what is the maximum number of leaves I can have? That is basically corresponding to number of leaves in a full DRE tree, and that number is d raised power n. So total number of leaves that I can delete while mapping each of these prefix free codes, this must be less than equal to d raised power n. So then I divide the left hand side and right hand side by d raised power n. What I get is this condition that summation d raised power minus wi sum over I to k must be less than equal to 1, and this is known as Kraft inequality. So what we have shown is, if there exists a DRE prefix free code, then we can map that prefix free code to a corresponding DRE tree, and we have shown that if a prefix free code has code word length W1, W2, W3, Wk, then this Kraft inequality has to be satisfied. Okay. Now we are going to show that if this Kraft inequality is satisfied, and if you have a code word of length W1, W2, W3, Wk, then this must be a prefix free code. So we are proving the converse. So suppose W1, W3, Wk are positive integers such that Kraft's inequality is satisfied. Now without loss of generality, we are just considering an ordered list of these code word lengths. So we are assuming W1 is less than equal to W2 is less than equal to W3, and which is subsequently W less than equal to Wk. Now let us consider the following algorithm. So start with I equal to 1, so we start with W1. Now choose Zi as the surviving node or leaf at depth Wi and prune the tree. So what we are trying to do is, we are given a set of code words which have length W1, W2, W3, Wk. And what we are going to do is, we are going to map these code words to this DRE tree. So how are we mapping it? We are mapping this code word Zi as a surviving node at depth Wi, and then we prune the tree. Stop if there is no surviving node or leaf. And this process will continue from I equal to 1 to k. Okay, so let us take an example. Let's say k is 3, and let's take W1 to be 2, W2 to be 2, and W3 to be 3. So what we are saying is, this algorithm is as follows. So first we consider an ordered list of code words of length W1, W2, W3, and we choose Zi as the surviving node at depth Wi and prune the tree. So here you can see Wk is 3, that's the maximum depth. So we will consider and again let's consider D to be 2. So let us consider a binary tree. So if we draw a binary tree of length 3, it will look something like this. So binary tree of length 3 will have 8 leaves, full tree. 1, 2, 3, 4, 5, 6, 7, 8. Now how are we going to map these code words of length W1 equal to 2? So what we are going to do is, so from the root you go at depth 1 and depth 2. I go here and then I prune all these leaves which are starting from this. So I prune this. So this is my code word corresponding to W1 equal to 2. Okay. Next I will look at this code word which is of length 2. So again I start from here. Let's say I go here 1, 2, so I delete this. So what I have here is, this is so I deleted those 2 leaves which were starting from this node, and if I consider W equal to 3, then I have this 1, 2 and 3. I can consider this. So this is W3 corresponding to 3, and rest are all unused. Rest are all unused leaves. These are all unused leaves. Okay. So to repeat what I said, to map each of these code words of length W1, W2, W3, what I do is, I first create a full DRE tree of length n, which is maximum value of Wi, which is Wk, and then I go at depth Wi, which is W1, W2, W3, and I delete all the nodes and the leaves or the branches which are starting from that particular node at depth Wi. Now if I am able to map all these code words of length W1, W2, Wk, then I will ensure that all the prefix-free codes have been mapped. So if we choose our ZK and we are able to construct a prefix-free code, then we are done. Then we are able to show that the code word is prefix-free, because there is a unique mapping of each of these code words to our DRE tree. So let us assume that Z1, Z2, Z3, Zi have already been chosen. So if they have already been chosen, then when I chose Z1, at that time I deleted this many number of leaves, which is d raised power n minus w1. When I chose Z2, I deleted these many leaves. When I chose Zi, I deleted this many number of nodes. So then when I am at point, I am trying to map Zi, how many leaves are left? The number of leaves which are left is, this is the number of leaves for a full tree, this is the number of leaves I have deleted to map I minus 1 code word. So the remaining leaves are then given by this. So this can be further simplified into this expression. Now please note, if the Kraft's inequality is satisfied, then we know from 1 to k this sum is less than equal to 1. In other words, if Kraft inequality is satisfied, then this summation would be greater than 0. What does it mean? That means there still exist leaves which can be deleted, and I can map my Zi. So you can see that if Kraft inequality is satisfied, this quantity is greater than 0. So I still so there are still leaves left. So there are surviving leaves left at depth n, which is greater than 0. And if I have leaves left in my prefix-free, in my DRE tree, I can always map my prefix-free code to such leaves. So if there is a surviving leaf at depth n, there must be unused nodes at depth wi, which is less than n. Why? Because there is one-to-one mapping between this DRE tree and prefix-free code. So if there are surviving leaves at depth n, it means there are unused nodes at depth wi less than n, which have not been chosen as code word by any of these previous code words Z1, Z2, Zi minus 1. And thus I can assign Zi to this particular node. And note, this condition will hold until I is k, because from Kraft inequality we know that from if j is 1 to k, summation di j is less than equal to 1. So in other words, what we have shown is then each of these code word of length w1, w2, w3 up to wk can be mapped to a DRE tree, and we know that if we can map these code words to a DRE tree, then they corresponds to code words of a prefix-free code. So hence we have shown that if the Kraft inequality is satisfied and we have code words of length w1, w2, wk, then this code must be a prefix-free code. Let us just take an example to illustrate how we can map a prefix-free code to a DRE tree. So consider a ternary prefix-free code. So ternary means d equal to 3, and these are my code word lengths w1, w2, w3, w4, w5. They are already ordered. You can see w1 is equal to w2 is equal to w3 is less than w4 is less than w5. So I already have these code word lengths ordered. So what is the condition for a prefix-free code to exist? the Kraft inequality must be satisfied. So, summation of d raised to the minus wi sum over I 1 to 5 must be less than equal to 1. So, you can see here, so this summation in this example comes out to be 49 by 81, which is less than 1, hence a prefix free code exists. Now, how do we construct a prefix free code? So, maximum code word length is 4. So, we can construct a DRE full tree of length 4 and then we start pruning it. So, we start pruning it for w equal to 1. So, all the branches which were starting from this node have been pruned, and this is a code word corresponding to this w11. Similarly, we have two code words of length 2. So, again this is length 1, this is length 2, this is length 1, this is length 2. So, the branches starting from these nodes have all been pruned. So, these are my two code words, and similarly you can see I have this is 1, 2, 3, and then beyond this point the leaves have been pruned, and I have one code word of length 4, which is basically 1, 2, 3 and 4, and the ones which I have shown by empty circles, these are unused leaves. Okay. Now, since this is a ternary code, so that you can see there are 3 branches leaving from each node, and I am just labeled them by 0, 1 and 2. So, this is basically my prefix free mapping of my prefix free code, a ternary prefix free code corresponding to these wi's. Okay. So, with this I will conclude this lecture. Thank you.